Okay, then let's start. So, welcome to the dark side of real-time. Today we will talk a little bit about Xenomai. My name is Richard Weinberger. I run a small company called Sigma Star gmbh. So we do mostly software development around Linux embedded and security, and also that's why I'm doing the talk. Often projects with real-time. And today I would like to show another approach how to achieve real-time with Linux, and maybe it's useful for you and you can use it in the one or other project. So the goal of this talk is adding Xenomai as one more tool into your toolbox, provide you with enough knowledge that you can start with Xenomai, and showing you another way how real-time is possible with Linux. The non-goals are, I don't want to promote Premium.t as their solution. Also, I don't want to promote Xenomai as their only solution. And also, I won't show off whatever awesome benchmarks with cyclic tests. Nope. But let's start slow. What is actually the main reason behind a real-time OS? So the main characteristics is that it's deterministic. So you know that in certain time frames it can do a certain amount of work. So you have to meet certain deadlines. Of course, these deadlines should be achievable in a reasonable time. So when your OS needs for everything 10 minutes, that's not good. So usually for real-time systems, the response time should also be fast in terms of micro or milliseconds. But it's not about speed in terms of throughput. So when people talk about real-time, they often talk about how fast something is. That's not the right word. It's more about, is it deterministic and does it guarantee to be always within the same time slot? And usually a general purpose OS like Linux is anything but a real-time OS. So Linux is general purpose. It's made for servers, desktop, or smartphones, but not real-time. But as we all know, Linux can do real-time, or you want it, and let's see how this was achieved. So as we know, Prim.t is now merged. This took a few days to get done, or years, whatever. So Linux is a general purpose OS, so it was designed for throughput and not really for real-time. But it did implement the POS6 real-time extension. That means it had the APIs that you can set a scheduling algorithm for example, SCAD5 or have the real-time priorities, but it never really enforced it. That was the so-called soft real-time mode. So Linux tried its best, but usually it didn't work that good. There are multiple ways how to make Linux real-time aware. The first option I always say to all customers, are you really sure that they want to use Linux as real-time OS? Maybe you can put your real-time workload under something small, a microcontroller, or maybe one of these remote processors like the PRU units of the ICE chips, or just keep it simple. Are you really sure you want to do real-time with Linux? Linux is a huge OS, it's fat, it has its issues, and not sure about it. When they are absolutely sure they want real-time with Linux, then you have the option use Preempt.RT. And Preempt.RT went the approach, okay, let's turn the whole Linux kernel into a real-time OS. That's a nice approach. It's the approach that made a lot of sense. It was also approved by Linus, and finally it got merged. But there's also a third option. This is the option I want to talk today about, is let's tame Linux using a co-kernel or dual-kernel. So put something in front of Linux that we can achieve real-time. And I still want the feeling of Linux, and this is Xenomai. But let's first talk about how real-time is actually achieved. You need to understand how this works and was done for example, Prim.t. I just forgot to set my timer, so no. So Linux is preemptible. That means Linux can interrupt a user space task at any point in time. That means when you run a while loop in user space, so while 1, then the Linux CPU scheduler can interrupt this program at any time and schedule another program. That's been like that since years. But when a program runs a system call and the kernel is entered, then it's not so easy. Then you had to enable the preempt feature that actually Linux can at some points preempt these tasks and shadow another one. And the main idea behind preempt RT is that you make sure that the running kernel code is at any time preemptable. And by any time, I mean any time. So at any point in time. This means, for example, also that your interrupt handlers run as regular kernel threads. Because when it is a kernel thread, then it's devoted to the CPU scheduler, and the scheduler can decide, has your real-time process a higher priority than the interrupt handler, then it can reschedule. And also, all these sections where you really disable the interrupts or preempt are minimized. So when you have a device driver that really disables interrupts for a long time, then your real time is gone. And all these drivers have been found and fixed. Also, for example, spin locks, so where the lock is spinning, have been replaced by so-called RT mutexes. So an RT mutex is basically a lock that has an owner. This allows you to implement priority inheritance. And of course, all kind of optimizations over the kernel, it took years. So, and finally, after 25 years of work, preempt RT is now mainline. That was a huge amount of work, and summarizing this into one slide is hard. And now let's talk about Xenomai, the other thing. How does Xenomai implement real-time? So first, what does Xenomai mean? Xeno means alien. Maybe you know it from Xenomorph, the alien movie, or xenophobia from a certain political parties. And Mai is just to make pleasant. So Xenomai is implemented on the so-called interrupt pipeline. So I will explain it shortly what the interrupt pipeline actually does. And it's this dual-kernel approach. That means inside the Linux kernel is another tiny kernel implanted, it's Xeno implanted, and it's called Cobalt. So with Xenomai version 3, it's called Cobalt. With Xenomai version 2, it was called Nucleus. So on a computer, an interrupt is actually the source of all kind of events. So whatever happens, it goes through interrupt. And a kernel that wants to make sure that its current work doesn't get interrupted and so has to disable interrupts. So all the critical sections run under disable interrupt sections, and this is how you implement locking or make sure that your code is thread safe. And the kernel, so Linux, has tons of these sections where it had to disable interrupts for a certain time to make sure that the data structures are consistent. Otherwise, multiple writers could have changed that. That also means as long as you disable interrupts for one CPU, you won't receive the timer tick on this CPU. And without the timer tick, there's no task scheduling. That means the CPU scheduler cannot schedule another task while that. And that's how you lose your real-time guarantees. And the basic idea behind the interrupt pipeline is that you have an out-of-band kernel, this is Cobalt, that will receive the interrupts at any point in time. And the in-band, for example Linux, can disable the interrupts, but it won't affect the Cobalt kernel. So when Linux has a critical section, it can disable interrupts, but it won't affect the real-time core, and the real-time core is still able to schedule real-time tasks. So when Linux, for example, is disabling its interrupts, then only the interrupts are virtually disabled. They are still enabled, they're still received by the real-time core, Xenomai, but Linux thinks it's disabled and it's all fine. So the interrupt pipeline used to be the ipipe batch. The ipipe batch is no longer maintained, it's dead. So the current approach is called Dovetail. So you have to be a little bit carefully when you read documentation or old blog posts or mails. I already used two words, in-band and out-band. So out of band means the real-time stuff, and in-band means Linux. But in the old documentation, the naming was different. It was the head stage and the root stage. So the head is in front, it receives all interrupts and can decide whether it wants these interrupts or not, and then later at the root, then Linux was placed and saw what was left. So Xenomai sits on top of the interrupt pipeline. So these days you need Dovetail. So Dovetail and Xenomai are actually two different pieces of software, and Dovetail is actually generic. You can also write your own Xenomai if you're funny. And there is actually something else. I will talk about that later. Here you see a small graphic. So the red bars are the things that are done by Dovetail. The blue bars are Xenomai, and the green bars are Linux. So when we receive an interrupt, then the interrupt pipeline switches immediately to out of band, and then it's decided, is this interrupt interesting for the real-time stuff, for example, the timer tick? If yes, then run the real-time CPU scheduler, then my real-time tasks are scheduled and run, and usually they run there until they give up or don't need the CPU anymore, or when they do something, I call it stupid, when they switch to the Linux domain. For example, when you run under the real-time load Linux system call, then you lose your the real-time guarantee, and then you are switched to so-called in-band, so to Linux. But let's go back when we switched. When we see that the interrupt is not interesting for real-time, then we switch immediately to in-band, so Linux. For example, when the timer tick is interesting for Linux, then the Linux CPU scheduler runs and you run your regular Linux load. And here see already this wanted by in-band. That means when Linux disables interrupts, then he would take the left branch. Then the interrupts are written to a backlog, and when Linux then later is re-enabling the interrupts, then they are replayed. This makes sure that Linux doesn't lose any events. But this allows also to implement critical sections with Linux. Otherwise, we will kill in Linux all kind of thread safety. So I said already, we have in-band, we have out-band, and these are basically two worlds. So in the Xenomai speak, this also means primary and secondary. So don't get confused by this other term. So just think about, we have two worlds, one world where all the real-time stuff can live, and one world we don't care about, that's Linux. So it depends on the point of view. So when you read the Xenomai source code, you will find that the term primary and secondary domain. Primary means everything real-time, and secondary means everything else that is not real-time. For example, Linux tasks. From the Dovetail point of view, also it's out of band. Out of band means real-time, and in-band is Linux. Since these are two projects, they're using different terms, so it can be confusing. But you can see here on top is the interrupt pipeline, then we have the real-time core, Linux core, and then we have tasks. And they are all just regular tasks. When I use the word two worlds, then some people think about hypervisor. So we have some commercial or open source hypervisors that can partition the computer in really the real-time OS and the non-real-time OS. This is not what Xenomai does. They actually share a lot of code, and from the Linux point of view, a Xenomai task is also just a Linux task. And you can also use a lot of code paths from Xenomai that are actually Linux, so they're really glued together. So it's very common that you have one process, and within this process you have some Linux threads and some Xenomai threads. That's the normal thing. But the crucial part is that your real-time task must only use Xenomai services. So for example, it must not use Linux system calls. It must not use file system I/O. Otherwise, when the real-time task is using Linux services, then it will trigger a so-called domain migration. Then the real-time task is migrated to the secondary domain, so to Linux. Then it runs under the control of the Linux scheduler, and your real-time guarantee is lost. So when you design an application that runs with Xenomai, it's really crucial that you make sure that the real-time thread stays already in the primary domain. And the guarantee from Xenomai is, as long as you stay in primary, all is good. Then the real-time is guaranteed. As soon as you switch domains, that's it. So That also means that the Xenomai offers its own set of system calls, its own set of device drivers. So for example, when you want to use real-time Ethernet, real-time CAN bus, SPI bus, then you need a distinct driver for Xenomai. That sounds now harder than it is. Usually it's not that hard to port an existing Linux driver to the Xenomai driver framework. They are not identical, but very close. Xenomai has also its own CPU scheduler, and one of the most important things is it also has a rich inter-process communication framework that it can communicate between real-time tasks and also between Linux tasks and real-time tasks. So the key is that you have the real-time workload in a real-time thread, but other things, for example, reading files and stuff in the Linux thread, and then have a real-time pipeline that you can exchange data between these threads. I said already, when a real-time task does something used from Linux, then it is switched to the secondary domain and your real-time guarantee is gone. And Xenomai has this so-called domain switch detection feature. So you can enable this, and as soon as it's enabled, then you will receive a signal that will tell you, okay guy, now you have lost your real-time guarantee because of that. For example, you will receive a signal, now you have switched to a secondary domain because you have used a Linux system call, or because you have triggered a page fault, or your thread ran away. So it did a while one loop. This, maybe from preempt RT is a real-time throttle. It's just a different approach. Also, it can tell you about priority inversion. But this is really, in my opinion, a killer feature, because then you will learn already while developing and unit testing your application that there are code paths that can trigger a domain switch, and you see it immediately. Otherwise, you have a lot of trial and error and measuring, and that can be hard. So now, what happens in contrast on preempt RT? I said already, preempt RT achieves real time because it is able to preempt a task at any time, and then it can schedule the real-time workload. But this is only when your real-time task is runnable. When your real-time task is not runnable, then it's not schedulable. Then preempting something else doesn't work. That means when your real-time thread under preempt RT is using file I/O or whatever other code paths that cause the real-time thread to be blocked and hence not runnable, then your real-time guarantee is gone. This also happens when a device driver doesn't behave. So when the device driver in the middle of the I/O control takes a lock and sleeps too long, then it's gone. And preempt RT doesn't really have a good mechanism to tell you about these sections. You have to do a lot of testing and measuring to find it. These days, there's something new. It's called runtime verification, and there's also the runtime monitor that can, to a given extent, help you with finding this, but this is very new, and have to admit I've so far not used runtime verification. It's on top of tracing, but it will help, but it's not so easy. But remember, with Xenomai, the guarantee is as long as you stay in primary, all fine. And that's a huge thing. Now let's talk a little bit. I hope now you're curious and want to try Xenomai on your own. How to start? First, you need a dovetail enabled kernel. So a Linux kernel where the dovetail patch is already applied. So you can clone directly from the Xenomai or the dovetail Git repo. For example, the latest one is 6.16. You clone this kernel, then you clone from the Xenomai project, and then the key is now you have to prepare the kernel with Xenomai. So because the dovetail is only the inter pipeline, and you have already to install the Xenomai kernel stuff into your kernel, and this happens with the prepare kernel script. So you change into the kernel source code and then just run the prepare kernel script, and then you can build the kernel. So using dev config and just build it. That's the kernel side. When you boot this kernel, then you will see two messages. First you see ERQ pipeline enabled. That means, yes, we have dovetail, we have interrupt pipeline. And then you see a little bit later that now Xenomai is registering itself to dovetail. Xenomai says, hey, you are the interrupt pipeline, I'm Xenomai, I will be your out of band stage. Make me fast. That's so far for the kernel. On the user space side, you also just download the Xenomai Git repo. It's the very same Git repo we've used for preparing the kernel. So the Git repo contains kernel code and user space code. Just the configure, make install thing. When you run make install, you get already a few demo applications. For example, the latency tool, it's the Xenomai pendant of cyclic test, but there's also cyclic test. This is really the cyclic test from the RT utils for Xenomai. Don't be afraid about the messy path, and when you say the same prefix and it just works, I was just too lazy. Yeah, and maybe we should set same defaults. So now how to use Xenomai in your application? So when you program a real-time application for preempt RT, you're just using pthreads. So there's no distinct programming API for preempt RT. For Xenomai, it's a little bit different. It offers multiple APIs. First, we have the API called Alchemy. This is the old native API from Xenomai 2. This has its own functions to create threads and all kind of this inter-process communication tooling you know from the old Xenomais. But it has also a POSIX skin. That means you can, as is, use your POSIX application where you create pthreads and compile it to use Xenomai. There are also a few other skins that are not so well maintained anymore. For example, one was or is still for VxWorks or for Pesos. They are rather old and helped porting VxWorks or Pesos applications to Xenomai. To be honest, I think these two will go away rather soon, unless somebody tells about that they really need it and want to maintain it. So Alchemy and POSIX will stay. I hope also Alchemy. So let's look at a very simple Hello World program. This is now using the Alchemy API. So we have our real-time task. We have the hello function that does a real-time printf hello from Xenomai. We create this task, start it, and join it. It sounds more or less familiar to the pthread API. How to build that? There is a tool it's called Xenomai config, and Xenomai config takes as an argument the type of programming API you want. So here it's Alchemy, and then we just say, please give me the needed compiler flags and linker flags, and you put it into your build system. So here I am using GCC by hand, but you can also make it print all the flags and you put it into your Meson script or whatever, and you just run it. On the other hand, the very same program as a pthread program. So here again we have our hello world, the main routine. Here we're just creating a regular pthread. We set the scheduling policy, we set priority inheritance, create a pthread, and that's it. And we compile it in the very same way. Oh, I skipped the slide, but we write here instead of Alchemy POSIX. I'm just missing the slide. It's gone. Sorry about that. So building Xenomai program is not that hard. I already said that Xenomai has its own set of device drivers. So these are drivers that are changed or simple enough to be real-time available. So within the Linux kernel is installed a new device model. It's called real-time drive device model. Using RTDM, you can create your own device drivers, for example, Ethernet, CAN bus, and SPI. As I said, usually you can copy them from Linux or also from a U-boot, just something simple. Sometimes it's a matter of a few hours, sometimes it takes a few weeks. So you can ask David, he spent the last few weeks porting a CAN bus driver to Xenomai. That was a hard one. But we also have a lot of them already. So we have many drivers for the i.MX system on chips from Freescale, also many for Intel, so it's not that bad. And we also have the so-called UDD framework. It's user-space device drivers. It's more or less UIO that you can create real-time device drivers in user space. But that's really something I want to highlight. That's really a maintenance burden. So these drivers are sometimes in really good shape, sometimes they are in bad shape, and sometimes there's no driver at all. So this can be work. So when you really need to communicate using, for example, CAN bus, you have to be lucky to find a CAN driver, otherwise you have to board it on your own. That's a huge benefit from preempt RT. There you have drivers for everything, and chances are good that these drivers will just work with preempt RT. I know you all wait that I show some nice graphics that Xenomai is so much better than preempt RT, but no, I won't. This may be because I'm a professional, maybe because I'm an asshole, I'm not sure. No. People often ask me to do benchmarks, and then they claim that the Xenomai is as fast as preempt RT, or faster or slower, and whatever. The thing is, cyclic test measures the wake-up latency. It measures how long does it take until the scheduler gets from a timer interrupt a real-time thread runnable. That's an excellent metric to profile and test real-time OS, but it's not really that what your workload does. And maybe your workload does something else. Maybe you have 3 real-time threads that communicate together and do something else that can work super good on Xenomai or badly on preempt RT, or the other way around. So when you try to compare Xenomai and preempt RT, please do it with your workload. So the chance is great that when you run cyclic tests on Xenomai and preempt RT, that the numbers are more or less the same. Usually the numbers in cyclic tests are a little bit better from Xenomai, but don't trust them too much. The takeaway is please benchmark your own workload, especially when you interact with devices, so with drivers. So the driver has a huge impact. And of course, Xenomai is no silver bullet. That means when your latencies come from the hardware, Xenomai can't do anything about that. So the SMI or shared caches or CPU deep sleep state would hurt you equally bad with Xenomai than with preempt RT. So when you suffer from that, it won't help, just to be clear. All I said so far applies to Xenomai version 3. But there's something new in the works that's called EVL. It's basically a complete re-implementation of Cobalt that broke with the existing Xenomai 3 feature, so new idea, fresh code. So libeval is just a few thousand lines of code. I think right now it's 20,000, which is much smaller than Xenomai is. And the cool thing is there's also Revel. That's a Rust API to the EVL core. So when you do real-time, then you often have to mess with safety, and when you can guarantee safety because I use Rust, buffer overflows are not possible, that's a huge win. And in the new version, there is also no more duplicated device drivers. So the idea is that you make the existing Linux drivers out-of-band capable. So for example, in a CAN bus driver, you're adding a fast path to receive CAN frames without sleeping logs, for example. So this is still a little bit experimental, but there are already fixed drivers and it looks good. And the idea is that Xenomai 4 will be again dovetail as interrupt pipeline, then on top EVL. So EVL is this rewrite minimal of Cobalt, and then on top of that libeval and a compat layer. So that a lot of old code will be thrown away or redone. So that's why I said by the skins, maybe some of them will go away, depends on their maintenance burden. So when you still use them, please tell. Often on the mailing list, Jan asks, is there still a user? And if not, it will be removed. Yeah. So I'm already at my summary, and my time is almost over. So preempt RT is fine in its mainland. It's awesome. But when you create a real-time application, keep in mind there's also something else. And maybe Xenomai helps you, maybe not, but I would like to show you Xenomai as one more tool, and when it helps, it's nice. So I fully understand that this concept with these two words and duplicated device driver is a high price, but sometimes it really pays off. And the cool thing is Xenomai is really fun to work with and hackable. So I already fixed the one or more issue, and it's really nice. And when you want to interact with the Xenomai community with a website, we have already Git issues, a mailing list, and there's also a bi-weekly community call without a typo, sorry about that. It will be announced on the mailing list, and when you have questions on Xenomai, just drop it into this call and ask questions. I will be around, and Jan also, we try to help. So thanks for your attention. I hope you learned something new, and if you have questions, go ahead. Yes, here.
Why does Xenomai require downstream kernel patches to the Linux kernel, and what's the upstream status for those patches?
So the question is, why do we need a patch, and what's the status about upstreaming that patch? Bad. Linus has decided that he doesn't like the dual-kernel approach. So Linus said the only way to do real-time is preempt RT, and now is preempt RT is mainline. So getting dovetail mainline is, I would not say impossible, but it's a huge amount of work. So and of course, also political work. The good thing is dovetail is now much smaller than the iPipe patch was. So porting this patch becomes easier. What's that noise? So I won't expect to have dovetail mainline in the next few years. But maybe Florian and Jan can tell about that a little bit more. No.
Dovetail alone doesn't make sense. But you have to have a user on top.
Yeah, so
the main problem, we don't have an entry user for that, so we would have to port at least Cobalt or EVL as well, and this basically doubles everything.
Exactly. So that's really a hard problem to solve, and I think it will stay out of free for a long time. So there's a question.
I might miss your explanation. My question is, you said the small kernel has its own set of device driver.
Yes.
What I'm curious about is it also has its own set of task scheduler, memory management system, or something else?
Yeah. So the question was what parts of the Cobalt kernel are on its own and which one are shared. I will go back to the slides and I find it. So Xenomai, actually Cobalt has its own CPU scheduler, but for example, it's sharing memory management with the Linux kernel. So
they use the existing memory management.
Exactly. Yeah. So that's why I said it's not a hypervisor approach, which is completely separated. So Cobalt is really part of the kernel and it's reusing a lot of the kernel.
But maybe some patches are required to exist right? No?
Yeah, I'm off the head. I don't know which sections of the subsystem are patched, but I'm very sure that Dovetail has a few modifications within
Thank you.
Yes, please.
Kind of debug facilities, or the insight in which threads are running, which of the Xenomai threads are running, how much ground is spent, everything you get with Linux for free. How do you do that?
Yeah, so for example, you can still use all the kernel tracing infrastructure. So the kernel function tracer is Xenomai and Dovetail aware. What is not doable is, for example, system call tracing using strace, because the strace tool knows only Linux system calls. But this issue is already being worked on, I think, by Florian, that you run all Xenomai system calls as part of the Linux PR control system call, because this system call has enough parameters that it can squeeze in these parameters all Xenomai services. And this would allow you to make strace Xenomai capable. But I fully agree with you, you cannot use all the Linux debug tools because they often don't know Xenomai. Yeah.
What architectures are supported by Xenomai?
Architectures. Right now, on the kernel side, x86 in 64-bit mode. On the ARM side, 32-bit and 64-bit, and RISC-V is more or less in the works. And LunArc, I think.
Waiting for active contribution on that.
Yes.
How would you evaluate when to use gmbh or Xenomai? So what?
Yeah. So the question is when I would use Xenomai and one primed RT. So to be honest, first I would try primed RT because it's mainline. And when my application just works, say with primed RT. When it doesn't work that well, and you get the feeling that muting Linux would help you, then you could try Xenomai, because the Dual-Kernel approach really allows you to mute Linux and stop all inflections from Linux. But then you have to be very sure that you can always stay in the primary domain. So when your real-time code paths are executing whatever, then you will always have domain switches and you can forget it. Yes, one more question?
Are there any requirements for the hardware in terms, for instance, segmenting? How many cores goes through Linux and how many cores goes through Xenomai in order to meet the real-time requirements?
So is the question how to separate the CPU cores?
Is it required?
Oh no. You can set the thread affinity like on Linux. You can just say this real-time thread runs only on CPU 1 and the other one on something else, but it's not really required. Yes?
Can you say a little bit about the memory between the Linux kernel and the Xenomai? So how does the Xenomai is using the memory resources in this arrangement?
You mean in the
Asks for memory, gets memory, and things like that. So you have something that is real time, is running.
Also, yeah. The question is how to deal with memory. So when you need memory in your real-time application, you can simply allocate this memory, but you have to pre-fault it. So and the Xenomai and Dovetail patch actually implement pre-faulting in the kernel. So when you allocate memory, then it already has faulted in. And this allows to use memory in the real time. So it works more or less the same like you would do with primed RT using the mlog all syscall.
There are things that in preempt RT that if you have, even if your tasks are the RT tasks and they are consuming certain kind of lock memory resources, you have the problem of others managing their resource, because the kernel, if it has to do memory free, has to lock everyone out, even if you have a RT thing. So it has to do its own housekeeping first before it gets the other one to run. So sometimes you have problems with even though you have RT5 for running, and you have RT preamp enabled, and your application is just a loop. If the kernel wants to do memory management for the rest of the tasks, then you're going to be suspended.
Yeah, but that's why you have to pre-fault all memory, that you can access the memory without interaction of the kernel.
So, yeah, so that's, I've seen that in the past. I've seen that, so the kernel will, even though you have a task that is, is consuming certain kind of resources, the non-RT task, they might have to do memory management, and then the kernel eventually would lock also the.
Yeah, so but when you share memory between real-time and not real-time task, and not real-time task does something stupid, then you're always in trouble.
So when the kernel has to preempt memory, it has to lock everyone out. So this is fundamental. It doesn't matter if you are running.
Yeah, but
Not the same process. Not of the same system.
yeah, you would never free that.
Yeah.
So
you change scheduling policy, if you try to use a deadline and things like that, so you get your tasks back to do a little bit of enhance the scheduling, to utilize the CPU more frequent when you want.
Yeah, but as far as I know, please, Jan, correct me when I'm wrong, Xenomai supports so far only SCAD 5 and SCAD round robin, so SCAD deadline is not yet supported.
Deadline not, but others are available.
Yeah.
But it's not a scaling problem that we're facing. It's really about the locking problem that you mentioned.
Yeah.
Also the main line. If you run on some content lock, then you're lost. That's something basically, this approach makes it easier. You can split these contentions more easily. And if everything goes wrong, split off the process, split off the cores, core affinity. So there's a lot of freedom there.
Yeah, so thanks for the questions. I fear we are out of time. If you have more questions, I will be around the next few days. Just talk to me. So.